Hello everyone, welcome to this finite element support channel. In today's video we'll see heat transfer analysis, conduction and convection. So we have given this 0.4 meter long steel rod. One end is exposed to high temperature and the other end is exposed to ambient or atmospheric temperature. So how the conduction looks like. So at the temperature at some distance from the first end, we calculate the temperature at each node. So we'll see in detail in this finite element in Abaqus as well as in analytical value. So let's see the problem definition, how it's looks like. So a steel rod we have given this material thermal conductivity property of 14 watt per meter Kelvin, so placed in 400 degrees C at one end and ambient temperature in the other end. So the film coefficient or convection heat transfer coefficient is there. We have given 10, and the length we have this. So what's our requirement is determine the temperature at each node at this 5 nodes. What is the temperature? Assume these nodes are equally spaced, so 0.4 meter, the length divided by 5 will get the distance between each node. So we'll calculate, we'll know the distance from one end to this end, from the first end up to the next point. So to do this, we'll graphically look like this. The initial temperature is there for this one is actually 400 degrees C, T2, T3, T45. How much there? So x1, x2, x3 up to x is equals to L. That is the distance is equals to the length of the rod. So analytically you can calculate the temperature T1 T minus T ambient over base temperature minus the ambient temperature, which is equals to cos hyperbolic m into length minus xi, where I is from 1 up to L, that is x1, x2, x3. As for we put step by step here. So the over cos hyperbolic over ml. Later on I will show you what m is in heat transfer. We'll see the highlights of how to derive this formula, how to derive this formula for H. So let's begin the model here. So before that, after calculating this value, what we'll do, we'll plot the temperature like this, how the temperature will vary, how the temperature value, numerical and analytical value will graph this way. So we have the length 0.4 length there, and the maximum temperature 400 degrees C there, which is given in one end. So how the temperatures moves down here. So we'll see this step by step. Let's go to the model and start. So create here put this the default value is 200, but put 0.1 because we have a small, we will see SI unit, you will use SI unit value. So 0.1 and go and create a circle with diameter radius 0.05 because we have given 0.01 in diameter, 0.01, so put 0.05 radius. Okay, then extrude up to length 0.4. Okay, let's define the material. With thermal conductivity I have given 40. Then create still sexy solid homogeneous. Then select the whole body and create assign the material, so it change to green. So assembly create instance. Okay, then in step we study on steady state condition. So in this procedure just click on heat transfer and response, select steady state. Okay, then go to interaction and create here interaction property, then film surface coefficient. In step select the whole body, surface film coefficient, how much the value, let's check, value is 10. Then end ambient temperature, that is sink temperature, put 30. Okay, then go to load, create boundary condition. So in step not initial, in step and in category other, go to temperature, then continue, then select this surface. So one surface, one end is exposed to how much temperature we are given, 400 degrees C. Then go to mesh, put in part, then mesh 0.001 for I think is enough, it's good enough. Can adjust here and select the material definition here. Standard by default it says how 3D stress, but you must select heat transfer because we are studying on that. Then mesh. Okay, then create job. Before that save. Okay, then submit. And wait for a result. Okay guys, the analysis completed. So go to result and see the value. We see how the temperature is looks like. Okay, before that let's see on calculation. Okay, here we have uniform cross section with small area dx with length and area cross section. So I have in and out temperature, that is minus k dt by dx measure at x up to x, then minus k dx dt by dx at x plus delta x. So this both sides multiply by a, that's area. In convection we have convection heat transfer coefficient times perimeter times T minus ambient temperature. So go to simplify this formula, then k dt by dx, this times area, plus k dt by dx times area, that's x, plus delta x minus h perimeter temperature minus ambient temperature. So simplify this formula, which is equals to 0. D by dx, which is at changing x approach to 0, d by dx dt by dx thermal conductivity times area minus h times p into T minus ambient temperature. So double derivative of temperature function with respect to x minus hp over thermal conductivity times area into T minus T ambient. That is, this hp over ka means m square. So m square is equals to under root of hp over thermal conductivity times area. So the formula for uniform cross section or rectangular cross section is equals to T minus T ambient over T base minus T ambient is equals to cos hyperbolic m into L minus x over cos hyperbolic m times L. So T temperature at specific node Ti is equals to cos hyperbolic m into length minus xi. Xi maybe x1, 2 or x3, x4. That's over cos h m times L, then base temperature minus ambient temperature plus this ambient temperature. So we calculate m first, that's under root hp over k times area. Perimeter is the perimeter of the geometry, circular geometry, so pi d, and area, cross-sectional area, because we have one-dimensional steady-state heat transfer, pi d square over 4. So we have given diameter 0.01 meter in SI unit, and thermal conductivity we have 40, and h we have 10. So substitute all values and we'll get m is equals to 10. Okay, proceed. So T1 is equals to cos h times m is 10 here, 0.4 length, that's length minus 0.08, that's the first node, 0.08 meter from, that is over cos hyperbolic 10 times 0.4, that's length still, times 370, that's 400 minus ambient temperature, that is 370 plus ambient temperature 30. Then calculate all of this value, then we'll get 196.47 degrees here. So in T2, in the same procedure, only you change the value of x, which is the next point is 0.16. So substitute this value, cos over cos hyperbolic 10 times 0.4 times 370 plus 30 Okay, we have done. We have calculated T1 and T2 in this case, so using this formula. So let's go to here. I'll calculate the temperature at x1 and at x2, and we'll left T3, T4 and T5 at the end. You can calculate each because the formula is easy and straightforward. You can substitute and calculate all the value. Whenever we have a number of nodes, excess number of nodes, you can use Excel, like use the formula here, like put the distance with 0 is there, that's the beginning, then 0.08, 0.16, which is when you divide the length by 5 division, we get this number. Then put the formula here, this formula which is cos hyperbolic 10 which is m times length minus x value over cos hyperbolic 4, that is 4 means 10 times 0.4 length times m times 370, which is T minus ambient temperature, which is 400 minus 30, so it's 370 there, plus 70. Then drag this down and you'll get 196.47. It's exactly equal to what we have calculated before. In the same way, when at x2, T2, which is 105.29 degrees. So let's go to finite element or Abaqus result. Here we have done, the job is completed here. So go to result, then go to section here, section, and not in this side, create in Z direction. So by default it cuts, divide the part into 2, but go to here manager, then from the length from the beginning up to T1 means, which is 0.08 meter. So but it starts from this end, so you can put here 0.32 there. Then this nodal temperature is, let's go to here viewport and annotation or toggle off those things except this legend, and remove dialog box and use this decimal places too, and put fixed value. So we have this 196.41. In the next, in this section, go to and rewrite this value 0.24, is that 0.24, okay, 0.24, which is the value 105.18 degrees. See, the next value is 16. So 64.76. Next, at x 0.08 47.85. And at the end you can measure here. At the end you have this value. So from this from the legend we have 42.99 degrees, the minimum value, which is go to from the contour you can understand the value here. So put 42.99, and this value is actually equal to the given value. So remove this cut option, then you have this one, 400 degrees. So we have this value, this finite element value and analytical calculation calculated value there. Then go to graph, insert, then put this section. X from 0 up to 0.04. Then in Y value put this analytical. Okay, in the same way add this numerical and put X value, then Y value is this one. Okay. Okay, here can reduce the maximum 400. The same way it's can reduce to 0.5, or you can leave it. So it's almost similar, because at the graph is overlap. Let's change one format here. So go to add, and here legend on the right can put, and other grid or any can customize based on your requirement, like this small grid. Then you can read the value easily. So here is how the temperature vary in different solution mechanisms, or analytical or numerical value or any experimental value. Compare the results in this way. This is all about today's video. Thanks for watching.